Okay, hello guys.
Hi.
Okay, so we have numbers and names number 18, and it is named the number of numbers. First of all, how's exercise doing? Any questions? How did you do?
Unfortunately, we haven't made much progress, but we definitely will.
Okay, time is running, so just don't.
When
When you're late, you forget, so that's.
No, you're right. You're right. I know.
Okay.
Okay, chat.
So the number of numbers. We had talked a lot about the numbers. So a number, like, maybe understandable for anything when you count something. Like, for example, the number of all particles, elementary particles in the universe, it's about 10 to the power of 80. It's 10 with the 80 zeros after 1.
Oh, in the universe?
Yeah.
80 zeros. So if you try just one other exercise, just try to write this number. All these 80 zeros. Just look at it. Write it for you and look at this number, okay? This is the number of particles in the universe.
But how do we know the exact number? How?
It's not exact number, of course. It's an estimate. So it can be done because we know the matter, the amount of matter in the universe because of the observations, astronomical observations, calculations, and everything. Okay? And you know how many like protons, electrons, and everything is inside, so we can estimate. Okay? So we can count chairs in your room, whatever. You can count this and that. So what is the number of the numbers? So we have numbers, right? In mathematics, different numbers. And can we count them somehow? What do you think? Eh?
Speak up.
I guess.
You guess? Okay. Any ideas how to do it?
No.
No. Okay. Okay. Let's try let's try simple number. 5. Can we count the amount of ones in 5, right?
5.
1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5. Right? So how we count? We actually put a label on each unit, right? The first unit, second, third, fourth, fifth. You know how to count, right? Easy. Okay, 5. The same number like n. Okay, we count 1 to n, right? Same thing. Now, so-called natural numbers, right? 1, 2, 3, 4, some number n. Can we count them?
Yeah.
Okay, so it's 1, 2, right? 3, 4, n, and then some infinity, right? So, easy to count.
Yeah.
And this is infinite amount, right? Some infinity. By the way, this infinity is called, has a special designation, and it's called Aleph Null. Aleph Null. X, not this is this letter, this Greek letter is called Aleph, so it's Aleph Null. Aleph Null, index null, 0. Okay, so this infinity is called like this. So when we count natural numbers, natural, right? It will be this. Now let's add to the natural numbers 0 here. What do you think? How many of them will be here?
Still infinity. Yeah, I agree.
You agree with what?
Vita. Still infinity.
Still infinity, yes. So how we count them? Okay, we put last. 1 would be 0 now, right? This would be second, 3, blah, blah, blah. Again and again. Aleph Null, the same thing. Let's go a little further. Okay. For example, let's count not natural numbers, but squares of natural numbers.
What?
Squares.
Oh.
So, squares. right? So squares. Square of 0 will be 0. Square of 1 will be 1. Square of 2, 4. Okay. Square of 3, 9, right? Blah, blah, blah. Okay. How many would be of them?
Would still be infinite. Yeah, it would still be infinite.
Infinite and what? Because we have labels,
Infinite
right?
square.
The same thing, labels like 1, 2. You see here is the labels for each square, right? Still labeled. They're still labeled. This process is called counting or enumeration. Oh, jeez, what is this? Enumeration. I'm sorry. Looks like. Okay, enumeration. So here are labels. 1, 0, 2, 3, and the same amount of Aleph Null. So again, looks like the same amount. Infinite, but same amount. Now let's try this. We have the axis, right? X-axis. And we have 0 here, plus 1 here, plus 2, plus 3, and here minus 1, minus 2, minus 3. What do you think? How many of them, of this point, will be on this axis? I mean only these digits, 1, 2, 3, and here minus 1. How many would you think?
5.
No, more. This goes
Infinity.
Infinity there, infinity there, right? So Aleph Null here, Aleph Null there. How many will be together?
Infinity still. No, 0. Because minus infinity plus infinity would be 0, but that's still infinity. So I don't get it.
No, the amount is not minus. It's still amount. You can count 1, 2, 3. Doesn't matter that it's minus. You still count them. You can count these numbers. You can count these numbers. So it will be 2 infinities or what?
2 infinity. No, but 2 infinity. It's still infinity though. Yeah, because 2 infinities it's still infinity.
It's still infinity, but what infinity? Is it the same infinity or something else?
Infinity 2?
Infinity 2. 2 infinities, right? Like 2 Aleph Null, right? Something like this.
It's rational.
Okay, so, the whole idea is how to count them. If we find the way how to count them, right? And to count, we just put labels on each of these things. So how we put labels? It's pretty simple. We start with 0, right?
Yeah.
This will be the first, 1. Then we go like this. Left, this will be 2. Right, 3. Again, left, 4. Right, 5. And together, right? You got the idea?
What do you count them?
We start from 0, and then we go left, right, left, right, left, right. So this is the first, then second, third, fourth, fifth. Okay? Here is 6.
Not how many numbers there are.
7. Yeah, how many? We're just counting. We're just counting.
Counting how many numbers.
Oh.
We're just counting how many numbers, plus and minus, right? How many of them? We're just counting.
Well, that's what they
So because they are labeled again 1, 2, 3, 4, it will have again this Aleph Null.
If you count
So
it's easy. Just go to the right.
so it seems maybe a little weird, but the amount of these numbers are still the same as natural numbers, and it's called Aleph Null. By the way, it's called countable. This is the term, countable. So all these sets of numbers, all of them are countable. They're all countable by the natural numbers, 1, 2, 3, 4, 5, etc. And the number is Aleph 0. Okay, let's try a little more. We have so-called rational numbers. Have you heard of this? Rational numbers.
I taught you this.
In the groups and groups.
Yeah?
Rational numbers are actually fractions.
Listen.
Oh. Rational numbers are fractions?
Yeah, fractions, yeah. So rational number is the number that you can represent by this. Like some number m divided by another number n.
Where m and n are integers.
Yeah, m and n integers, yes.
Isn't there a definition of a fraction?
Yeah, exactly. It's a ratio. That's why it's called a ratio.
And the same thing is called rational number. This number, when you divide it, it's called rational number. So what do you think? How many of them?
How many
Infinity.
But which infinity?
Again, infinity, but can we count them somehow again?
Talk. Walk with Zeta.
Uh-huh.
Wouldn't it be infinity too? Because there's different infinities. Doesn't the second infinity count rational numbers?
Second infinity, first infinity. Let's try this. M and n, right? So, like for example, m is like this, maybe 1, 2, 4, whatever, 8, 9, right? Some number, right? And here we have another number, 3, 5, 8, 0, 9, whatever. You have pair of numbers, pair, up and down, right? We don't know how many numbers can be here. The infinity here, yes. But can we count them somehow? Any idea?
Maybe you can try to think of the numbers at the top as positive and numbers on the bottom as negative.
Yeah.
And use the same kind of trick.
Okay, you got the idea, right? So just count like this. This is first, this is second, this is third, this is fourth, this is fifth, this is sixth. And like this go up to the end here and here. If this finish first, we count here. If this finish first, we count here. But anyway, this is just the same count and the same amount. 1, 2, 3, 4, 5 up to, again, Aleph null. It's pretty interesting, but rational numbers amount, the number of rational numbers are the same as natural numbers. So the same amount everywhere. And there's interesting thing. There's interesting thing. Let's imagine that we have a hotel or Grand Hotel.
We own it?
Yeah, you own it, right? Grand Hotel. It's very
What
nice.
is it? I know this.
Oh, you know this. Okay, good. So the
I
Grand.
know. I read it in the book. This is a paradox.
Yeah, and there's no vacancies in this hotel. It's all full. No vacancies.
Can I say it? Can I say it? No, be quiet.
Okay, let's still do it, okay?
Predict.
So we have person 1 living in room 1, right? Person 2 living in room 2. Person 3 living in room 3. 4 living in 4, and etc., right?
Yeah.
So and you have, of course, you have Aleph null of the rooms, right? And Aleph null of people living there, right? Same amount. Now let's do certain thing. Imagine that there are more people come. We don't have any vacancies, but we do some interesting thing like this. We put this first person from here. We move it here to the second.
Oh.
But here lives already person 2, right? So we move person 2 to the 4th room. And person 3 the same, right? Because some person lives here, right? So person 3 and here. Person 3 we put into the 6th room. You see, so all persons are putting here. No, we remove from each, we remove the person. Like person 1 moved to room 2, right? But room 2 is actually emptied because the person 2 goes to the number 4. The same thing with 3 goes to the number 6. You see here? And 4 goes to number, what do you think? Huh?
5.
3 goes to 6, 2 goes to 4, 1 goes to 2, 4 goes to
8.
8, right. So 4 goes to 8, and if we have person number n, it goes to the room number
2n.
2n. Right. And you see after this interesting procedure, right? We have
There are vacant rooms.
we have room. This room is empty. This room is empty because all of them gone. This room is empty and many rooms. And how many rooms are empty now?
1.
What do you think? So this is first room empty, right?
Did the n?
Okay. This is second room empty, right? This is third room empty. Blah blah blah. Okay, here before 2n there's 2n minus 1. 2n minus 1 is empty too. 2n is filled, right, by the number n. Next is empty again. So how many? 3 rooms now. No, not n. Let's go to infinity. And we can count this infinity. 1, 2, 3, etc.
Infinite. Oh yeah, infinity.
And infinite, what infinite?
Infinity.
Huh?
No, not of infinity.
Oh.
Yeah, it's a countable thing. So again, it's aleph 0.
Exactly.
Aleph null. So aleph null. So we have them no vacancies before. Then we make this weird move, right? Move of all the people, and we have empty for rooms with a number again aleph null, infinite number. So can we do it again? Because the new people come, right? They filled all the empty rooms, right? Now all of them are filled. By the way, what's the amount of the rooms? It doesn't change, right? It's still aleph null. So it's already filled now. And can we do this process again? The new people come. Can we?
But yeah, I don't know.
Yeah, we can. The same thing. They were filled before. They fill now. The same story. So we can do it again. We can do it again and again and again and again. So infinity is a very weird concept, actually. You see, right? So whatever we do in these rooms, right? They still can be emptied. And there's infinite amount of vacancies appear to be, and we can fill it again and move them again and again and again. So this is called Grand Hotel paradox of Hilbert. David Hilbert, I mentioned this guy. He's one of the great mathematicians of 20th century, the beginning of 20th century. So in this case, let's talk a little about sets, right? You remember, right, what set is, right? Set is a many of something, right? And so with this infinity, you see, with this number aleph null, right? You see that these infinity numbers are actually have sets. The set of aleph null, like maybe 1, 2, 3, right? 4, and can be 1, 4, 9. Remember squares, right? 16. And this is called subset because in this set, in the set of doubles, there are no numbers 2 and 3, right? Here they're present, and here they're not. You see? So this is a subset. It's called subset because all these numbers belongs to this. All of these numbers belongs to this. They're here somewhere, right? We can find them here. But not all of these numbers are here. So this is a subset of this set. And still, the amounts are the same. This is aleph null and this is aleph null. So they're both countable. Think about it. Pretty interesting thing. So now we see that lots and lots of things, right, can be countable. You see lots of them.
Yeah.
So are there some sets that are not countable? What do you think? There are some numbers, maybe you remember the name, like p, like pi, right?
Yeah.
It is called irrational.
Daddy, isn't it irrational because irrational numbers are infinite decimals?
You know that rational numbers, like if you try to divide 1 by 3, right? You will get this 3, 3, 3, infinitely too.
So then it's irrational.
But this is rational because it's divide, like one number divided by another one, one rational number divided by another one.
Irrational because it cannot be represented by a ratio.
Oh.
Yeah.
Wait, is
Yeah,
it
that's
ratio?
good thing, yes.
What Dedek has over there?
So this is ratio, right? This is ratio, fraction, right? So irrational is not represented by ratio. So p is irrational, like lots of other numbers are irrational too, like a square root of 2, right? Or a square root of, I don't know, 8. No, not 8. Yeah, 8. Whatever. So many of them are irrational, and they are, yes, they are infinite, like pi is, like this 3, 1, 4, and something. Antosha, I think you remembered some, right? Lots of numbers of this.
Okay.
Some days ago, right? So it goes infinitely. So what can we say about these irrational numbers? Okay, they are not rations. Looks like they are not rations. It is proved that they are not rations, but can we try to count them? So how they are count? And there was one guy whose name was George Cantor.
Me too.
He lived in about 1800 something. Don't remember the year exactly. At the late 80s, he discovered a theory which is called set theory, or theory of sets. And one of the things there, he managed to count these irrational numbers. Not managed to count, but he proved some theorem, interesting theorem. And the theorem goes like this. It is called Cantor's diagonal method. He used the method of proof, which in mathematics is called reductio ad absurdum in Latin. Reductio ad absurdum. So it's the way of getting some contradiction in the proof. If you're proving something and getting contradiction, it means that the proposal that you actually suggested is wrong. Something is wrong there. Should be no contradictions like in mathematics. At least that was the main thought in the beginning of 20th century and the end of 19th century. So there should be no contradictions. If you come to contradictions, then your statement that you put, like statement P, is wrong, so false. Right? So if it's false, then negative of P is true. So if it's false, so negative is true. This is the idea of this proof, reduction ad absurdum, or getting to contradiction. So that method he used in his Cantor's diagonal proof. So what he actually thought of? He wrote some, for example, some irrational infinite numbers, and starting with 0, for example. So 0, like 1, 3, 4, 5, 8, 0, whatever. Then this is the number 1, right? Then he put another number, like maybe 2, 0, like 5, 7, 9,
Wow.
whatever, right? And again, 0, like maybe 5, 8, 2, whatever numbers. And he suggested that all of them are irrational, or something like this.
Oh, yeah.
So it goes infinitely there. And he suggested that he wrote all of these irrational numbers, all of them, each and every of them.
Infinite.
Yeah, infinite. It goes infinitely there,
Irrational.
goes infinitely there, and goes infinitely there.
Okay.
And he said, okay, let's and of course, if you go to infinitely there, you can count them. Remember how we count them, right? So this is first, right?
Mm-hmm.
This is second, this is third, this is fourth, and and aleph null, right, to the end. So he suggested that maybe we can count all these irrational numbers. Why not? Let's try that. And then he said that, okay, let's do something. Let's write number like this, by diagonal. It's called diagonal. So take this number, then diagonally take this number, then this number, then here number, this diagonal. You see?
Yep.
Goes like this. And let's write it. Let's write it. This number, right? But change each digit. We change with the law like this. If it's 1, it goes to 2. We change 1 to 2. If it's 1 anywhere, and if it's any number other than 1, any other, but not 1, is changed to 1. Not 1. And write this diagonal thing. So here, the first number, what would it be according to this law?
2.
2. Second,
It would be 1.
1. Third,
1. Oh,
1.
no, 1.
Right, 1. Another one, this left, for example, 0. Okay?
It would be 1.
1. And so some number, right? We get some number, again, infinite, like all of them. Let's look at this number. This number differs from any number of this list because this digit is changed, right? So this number is not coincide with this number. For this, second digit is changed. It's not coincide with this number. For the third, here digit is changed. So it's not coincide with the third. And then you can go to all of these numbers, right? And this written number, diagonal number, right?
Yeah?
It is not identical to any of this list. So what we have? We looked at, we count all of them, right? But now we found something that does not belong to this aleph null. We found some other number.
Mm-hmm.
And this means contradiction, yes, because we thought our first proposition is that we got all of these numbers. And now we find another one which does not belong here. It means that the proposition that we count these irrational numbers is just wrong. And then was born the idea of non-countable or uncountable numbers.
Oh my God.
And the first uncountable number was called, any idea how it was called?
K.
Uncountable number. The countable is aleph null. And uncountable?
Oh, uncountable. No, next one.
Uncountable?
No, aleph null is the countable set. No. Aleph null is the countable. What's the aleph 0 is the countable. What's uncountable? Aleph 0?
Just notation, guys.
Aleph 1.
Aleph 1, yeah. Aleph 1. Exactly. And this aleph 1 was proven, not proven, but it's called continuum number. So x aleph 1, it is called continuum. So you heard the name continuum, you know now that it is Aleph 1, this is the number Aleph 1. It's infinite, and it's proven that this, the infinite, it is so infinite that it infinitely bigger than Aleph 0.
But that's weird because they're both infinity.
They're both infinity, yes, but it's infinitely bigger than, oh.
But the weird part is that they would still be the same.
No. Interesting thing that it's uncountable, remember? We cannot count it. We tried to count it and we found another number, which is we didn't count. You see this contradiction? We count, we suggested that we counted them. We counted them to the end, to the Aleph null, right? And then we see that it's not countable because we find another number, which is not counted. But we already counted them. This is a paradox. This is a paradox, yes. You got the idea?
Yeah.
No, я ничего.
So, Rome in Kingston.
Yeah, okay. So, there come, later, there come the guy whose name is, again, some Austrian guy. Yeah, by the way, this George Cantor was Russian-German, by the way. It looks like that he lived in Russian Empire. Another guy whose name is Kurt Gödel. And sometime around 1931, he proved a theorem, actually, which is based on these ideas of countable and uncountable. I'm not going to prove it, of course, but because it's a little tricky for your age, right? But in general, what he does, remember we spoke that actually mathematics is a language, right? So you can write any mathematical expression like with using special symbols, right? And using the alphabet, right? Any symbols, like symbol of function, right? Symbol of square root, blah blah blah, x. So there's a certain amount of symbols, not infinite, finite amount of symbols. So we have some alphabet in which we write any mathematical expression. The same thing we can use instead of this alphabet. We can use numbers. We can use numbers, right? Like this symbol we designate, we denote like 1, square root like 2, right? Like x by maybe some 5, whatever. So all these alphabet symbols we can designate like as a number. Designate as a number. So just a notation. Because mathematics is a language, sort of using alphabet, we can use different alphabet. 1, 2, 3, 4, whatever. And if we use this alphabet, we come to a certain interesting thing. If we have certain set of axioms and certain set of proofs based on these axioms, right? Some logical proofs of theorems, right? Using these numbers, we will write these proofs as a long numbers like this: 1, 2, 5, whatever, 9, 0, 5. Then another, it's the first proof, right? Then the second proof, 3, 2, whatever, number. That's what he did. He changed the alphabet and wrote all mathematical expressions. The list, like he suggested, that there's a list of all proofs based on certain set of axioms. All these proofs, right?
Yeah.
And he did the same thing. He wrote all these proofs with the numbers, and then he see that he can count them, right? 1, 2, 3, right?
I see it. Yeah, I can see it.
And with the suggestion that he can count them, again, he created this diagonal number, which again is some mathematical expression based on axioms, but is not, but it doesn't have proof because all the proofs he has already in the list. The same thing can be made with the unproofs, so something with which totally not only true, but totally false.
Wait, hold on, I don't understand.
Yeah.
He's saying that the number of theorems in math is uncountable?
I think it's countable.
No, not the number of theorems. Number of theorems is countable.
Yeah, that's right. That's wrong. That's what I'm saying. So I don't understand.
That's exactly. I'm saying exactly that. It's countable. Yes.
Okay.
Yes, but the interesting thing that when you imagine that you can write all of them, so count all of them, right?
Yeah.
You still can find something else, which is how it is called, correct grammatically and everything, right? But it cannot be proven because it is not in the list of proofs. We already got this list. And this number or expression does not belong to this list.
But then can't you make a bigger list of proofs?
You already made it. That's the suggestion. That's how the proof goes. So you made a list. You think it's full, right? So everything is this list. And you found some expression that is not in this list actually. And he not only did that, he actually constructs directly some statement, some phrase, right, mathematical phrase, which is constructed correctly, but cannot be really proven. And any idea what kind of origin he used to make this expression, which is not provable? It's not true and not false. So he constructed. This is one thing that he found out, that there are some expressions that does not belong to the list of proofs and unproofs. But actually he find directly some construction that actually does not belong here.
Maybe
phrase. And which is, yes, say what?
Maybe he found one expression and you just do the opposite of it and see if it works. Yeah, isn't that how these Russian guys invented new things?
Okay.
Yeah, that's actually what Jerry taught us before. How to invent things.
I know.
Yeah, okay. Okay, so not true and not false. Yes, okay, but he didn't know this method, right? It was it was in 1931, right? This method was not there yet. Anyway, but he constructed certain thing. It is called named Gödel. It's called Gödel sentence or statement. Sentence or statement. So, what do you think? What he took as the origin of this? So, how he managed to construct it? Just any idea that he need to construct something that is not true and not false, or it cannot be proven? Is it true or false? What do you think he used?
I don't know.
We talk about this a lot. What is not true and not false? Or at the same time, true and false?
Paradox?
Yeah, paradox, right. Paradox, yes. He took paradox. One of the paradoxes known for mathematics to that moment already. They were found, remember I told about this some time ago? And he used it as a base for this sentence. So the core of this sentence is an actual paradox. And the paradox was like this. It's pretty famous paradox in mathematics. And we talk about this. The origin of this famous paradox, it is called Barber's paradox.
Whose paradox? Oh, Barber's. Oh yeah, Barber paradox.
Barber, remember? Right?
Yeah.
The guys who shaves everybody who does not shave himself, right?
Yeah.
So, but he took us this, but he formulated it in mathematical way first. I think it was not even Gödel, but anyway, it was And this sounds like this in the language of sets. So let's take a look at something we call R. R is a set, right?
Russell's paradox.
R
Dana,
is
this is Russell's paradox.
right. Oh, you know Russell's, right? Again, Russell's paradox. Exactly. So you heard about it? Papa told you?
No.
Who told you?
No.
You read it yourself?
I was reading
Uh-huh.
a math book, and then I found it so interesting. I did a presentation on it.
Oh, great, congratulations. So just repeat for those who didn't read this book, right? Okay, this R is set of all sets, set of all sets that are not members,
Not
members, or subsets, you may say, not members of themselves. Uh-huh.
It's sort of like this. Same thing, like let's keep R as a set of all sets, or R is a set of all sets that don't belong in these sets. So it's stating that these sets that don't belong in it.
Yeah, you may say it like this. Yeah, little formulations of maybe a little different, but it's the same thing. That are not members or not subsets of themselves. Member is just something that belongs to the set, right? Member of the set.
That's true. That means that those sets would belong.
Yeah.
But then they don't because they don't belong. Exactly. That's why it's called Russell's paradox.
Mm-hmm.
Hey, Dad.
Yes.
Dad, this is also the exact reason when you said about the story of those guys that committed suicide. Because I spent the whole time making these books, and Russell proved it that you can make paradoxes with math.
Yes, right. But this was not only one paradox. The Russell's not a single paradox. They found many paradoxes at the time. Yeah. So there was a big story on this.
Those guys should have.
Interesting enough that mathematicians, they were digesting these ideas of this Russell paradox and Kurt Gödel's theorem, and there are other theorems of this pretty famous. They're connected all together, many of them, like Church-Turing, different theorems, and they were digesting for the 100 years. For the whole 20th century, they were trying to understand what is going on, because they believed so much that mathematics is. There is no contradictions in mathematics. Mathematics has no paradoxes, nothing like this. And suddenly they found dozens, and actually infinite amount. For now, they're coming to idea that something really big happened, and now you can find these things even in Wikipedia. Just maybe a few years ago, you would not be able to find it anywhere except the special books, special manuals for this square mathematician hats.
Right. I think this follows from what you said earlier, that math is countable, which is true. But in between you find the paradoxes, and that means that they're uncountable.
But that's not only one. The problem is that mathematics is full of paradoxes. It's not about one paradox. That's one famous one, yes.
Right, I said uncountable. So that's not only infinite, it's uncountable.
So you want to say something else? I'm not getting.
No, that's it.
Oh, okay. So no questions on this. You got the main idea, right? So this is. So now you know at least something. Of course, we may say that after Aleph null, right? What is this with it? There is Aleph 1, right? And do you think are there others? Aleph 2,
3, 4, 5.
and each of them is greater than the previous one infinite times. Each of them. And these numbers, they are numbers, like, because they're amount of something.
There is countable number of infinities.
But that wouldn't. That doesn't make sense. But no,
Probably yes. Here in this thing, that actually George Cantor found. Yes, he suggested that they are cardinal numbers. Actually, he suggested even the certain arithmetics on them. So how you can add one to another, multiply, something like this. So, but this is long story. But the modern mathematics mostly it deals only with Aleph null and Aleph 1, which is called continuum, right? This is countable, and this is continuum. And we, in modern mathematics and modern physics, we never go even to this Aleph 2.
But then,
Yes?
But then technically countable infinities are uncountable because you can't count it up to infinity.
Each of them are uncountable. Aleph 1 is uncountable. Aleph 2 is even more uncountable, right? The only countable infinity is Aleph null. Aleph 0, right? Aleph null. Those numbers are called cardinal numbers. The name comes from Cantor. And their numbers, of course, they're all infinite, right? But actually, the modern mathematics deals only with two of these cardinal numbers, Aleph null and Aleph 1. All the others are somewhere in space, you know. Nobody knows how even to use them, really. Cantor suggested some arithmetics with it, but that's it. Nobody knows what it actually does. So they know that there are certain numbers and they know what to do with them. So he suggested some way to count them, right? There's also what time is it now? Yeah, okay. I think we should finish. There's also some just for you, one thing. There's one guy in 20th century whose name was Neumann. He's a German-Austrian, I forgot, German-Austrian Jew, son of a banker, which was given by the king. This von, this is aristocratic name for certain money that he gave to the king. His father of von Neumann, and von Neumann is a pretty famous mathematician and physicist. So von Neumann suggested some idea how to create these cardinal numbers, and the interesting thing is about it that he created all these sets of numbers out of one thing, which is called empty set. Empty set. Yes. Empty set is a set which does not have anything.
But then how did it sort of makes sense?
Yeah, that's pretty paradoxical too. So we may talk about this a little later. So, but just you think about it, that how can be done? But he created the whole thing, all these numbers, out of just empty set, almost out of nothing, right? That's one interesting thing. Again, he did it, by the way, to overcome these paradoxes, which he failed actually to do. He didn't overcome them, but he was trying to. So he created everything out of empty set. He wanted to create whole mathematics based on this empty set and all that kind of things. Pretty interesting attempt, but it failed. Okay, so any questions on this, guys?
No.
Okay, so then take a pen, the questions, right? Ready?
Not yet.
Uh-huh. Okay. So give your own countable infinite subset of natural numbers. Your own example.
Own countable.
Your own example.
Set. Yeah. Own infinite.
Own means your example.
Countable
infinite subset of natural numbers. Your own idea. Any subset. Okay?
Okay.
Second, Take a look at Russell or Barber's and Liar. Remember Liar's paradoxes? These three. Barber's, Russell's, and Liar's paradoxes. Look at them and try to find any similarity.
Okay.
Are they somehow, maybe they connected somehow? And the third is create your own paradox. New paradox. So using maybe invention ideas, you know, this that we talk, how to make inventions. Create new paradox based on any of Russell's, Barber's, Liar's paradoxes, but the paradox which is used this opposition, one, many. So one is opposed to many, and many is opposed to one. Many consists of one, many of one creates many, right? So look at this, think about this paradox and create
I don't know what this means.
And create your own paradox.
I don't know what this means. One to many, what does this mean?
No, you know what many means, right?
Okay. Stop the rust.
You understand that it's connected with the sets. Of course, many, it's very close to the set, but still, many is about numbers, right? Many. Like for example, number 5, right? It's 5 of ones, right? Right? So 5 is many and ones is one. So just think about it and try to create paradox with these terms, one and many, based on these paradoxes that you know.
I'm sorry, I still don't understand. Well, what does it mean one to many? I don't get it.
You got that as a position, right? Many is opposite to one.
Okay.
And one opposite to many, many opposite to one. They are not the same. So just try to form your own paradox. So put this, I mean, say it like this. Put relation between one and many into the form of paradox. So make it as sharp as paradox. So create your paradox based on this relation, one and many. Opposition.
Okay.
That's creative question, so just think, invent, and then we may talk at a certain moment. Okay? Any questions? Any more? Okay, guys. So see you next week. Have fun.
Okay, thank you.